left. Before we left for break, we did anti-derivatives, right? This evening, we're going to look at the most consequential results in Calc 1, one of the most important results out of all of calculus. And this is the crux of Calc 1. Fundamental Theorem of Calculus. It comes in two parts. And depending on the text, the parts may be flipped. So the first part relates derivatives and integrals. So we have a continuous function, small x, on a closed interval a to b. A function big F is defined to be the integral from a to x of little f of t dt. Big F prime of x is just little f of x over the interval. The second part is generally known as the evaluation part. It gives us a way of evaluating integrals without having to form a Riemann sum. Right? So again, the left continuous over the closed interval a to b. Let big F of x be any antiderivative of little f. The integral from a to b of f of x dx is big F of b minus big F of a. An important key word here, any antiderivative. Right. Remember, there's an infinite number of antiderivatives because you have that constant. So generally speaking, what we do when we use the evaluation part is we take what's called the simple antiderivative. I think I mentioned that. And that's the one where the constant of integration is 0. There you go, section 5.3. Fundamental Theorem. We do cover 2 sections today. We also do section 5.4, which is on net change. So if we're looking at the integral of a rate of change, then that integral actually gives us what's called the net change. All right, so there's 2 ways of representing it. First way is to say that f of b is f of a plus your change. Right, the change is the integral from a to b of f prime. Rearranging that, you just get the integral from a to b, f prime of x dx is f of b minus f of a. So this is saying that the definite integral represents a net change. Well, we said, remember, the derivative was a rate of change, right? And now the integral represents a net change or a total change, right? A total. Well, those are two very useful quantities in applications, right? So they occur a lot. Totals in particular occur a lot. Right, so do that. Now I'm only really introducing this. We're not really going to work with it. But I did introduce the mean value theorem earlier. Well, this is the mean value theorem using integrals. Again, this is a pretty important result. F is continuous over the interval AB. Then there exists some point C in your interval, so that f of C is equal to 1 over b minus a times the integral from a to b of f of x dx. So that value there, that expression on the right-hand side, is average value of your function on the interval. With that in mind, what this theorem is saying is that for every continuous function, there has to be at least one point in the interval where the function takes on its average value. And so the function has to take on its average value at some point over an interval. That might be examined more closely in Calc 2. So let's compute this integral. And this is a simple integral. You can either verify it using Riemann sums or geometry. Fundamental theorem says, first, find an antiderivative. So go term by term. What is the integral of 2x? What about of 1?
Minus x.
And we take the simple antiderivative, so we take the constant of integration to be 0. Now evaluate that from 0 to 3. Two ways to do it. So you can treat that entire x squared minus x as big F of x. Right, so then you just evaluate that at 3, evaluate it at 0, and subtract. I prefer to use the linearity property and just do each term individually. So I'll just do x squared from 0 to 3 and x from 0 to 3, and then add or subtract the results as necessary. X squared 0 to 3, what's 3 squared? What's 0 squared? 9 minus 0. X from 0 to 3, this one's difficult. 3 minus 0. 9 minus 3. They equal 6. And again, you can easily verify that. That's the fundamental theorem. G of x is defined as an integral. Integral from 1 to x, root t plus 3 dt. They want us to find G prime and evaluate it at 1. Well, this is a part 1 problem. The function is defined as an integral from a to x, isn't it? Oh, that makes this really easy then. There's G prime. Now just evaluate it at 1. It's just 2. Oh, it can't be that easy.
Yes.
It is. Now we can throw some speed bumps in there. Now we have integral from 0 to x cubed, 1 over 1 plus t squared. Find h prime. Well, that is not a to x, is it? No, it's not, right? That's okay, because we have a nice little rule called chain rule. For this one, I'm going to explicitly write out what I'm doing. We're essentially doing a change of variable and saying u is x cubed. Now we're a to u, right? Now fundamental theorem applies. And then chain rule times u prime. But u is x cubed. So what's u prime? What is x cubed squared? To the what?
6, right?
To the 6. There's h prime. So it's small speed. Although generally the smaller speed bumps are worse on your suspension system than the larger ones. The worse are the really tall ones that make you scrape go over it, no matter how slow you go. Okay, looks like the sun's trying to come out. They lied to me though, they promised me heavy snow.
Isn't it terrible?
We didn't get any.
Washington, New Jersey. Maybe go north.
I got an alert as I was leaving for work. Heavy snow soon. And heavy snow the further north you go. Yeah, I live like 45 miles south of here. So I was expecting not to snow. I see nothing. I'm sad.
Just one puddle.
I'm sad. I want snow so I can throw my kids into it, run away. This one presents a bit of a problem. If you look at the fundamental theorem, technically speaking, A has to be less than B. Right, because it's the interval A to B. We don't have that, do we? So fundamental theorem doesn't really apply. But we can fix it. Can I just write that? Switch the limits, multiply by a negative. Now fundamental theorem applies. Again, am I going to do that all the time? Probably not. I'll just do the f of b minus f of a, where a is the lower limit, b is the upper limit. It'll give me a negative anyway. Just to make life easier, let's just distribute that negative further. Now fundamental theorem applies it. Thank you. It states, first, find an antiderivative. What is the integral of 3x minus 4? So we just ignore the constant, evaluate that, now from negative 1 to 2. 2 squared, negative 1 squared, 4 minus 1. 2 minus negative 1.
3.
Factor out that 3. What is 3 halves minus 4?
Minus 5.
Now multiply that by 3. The integral is negative 15 halves. Average value of x squared plus 1 on the interval 0 to 2. So the notation is going to be f bar. And I personally just like to include the interval. So this is the notation I use. Sometimes you see that as a subscript. Sometimes you just don't see it at all. It's kind of implied in the problem. But I'll be using f bar 0 to 2 to represent average value on 0 to 2. 1 over b minus a. Right, so 1 over the length times the integral from a to b f of x dx. Integral of x squared plus 1.
X cubed over 3 plus x. Plus 0.
Two cubed. 0 cubed. 8 minus 0. And that will be times third. 2 minus 0. What is 8 thirds plus 2?
14 thirds.
Times a half.
7 thirds.
Average value of 0 to 2 is 7 thirds. Particle has velocity of 3t minus 2, measured in meters per second. We want displacement along the interval 1 to 4. So displacement would be delta S, right? Change in position. What's the rate of change of position?
The derivative? Or
Which is what? Velocity, yeah. This is a net change problem. Because that will give you S of 4 minus S of 1, which is change in x. What is the integral? 3t minus 2.
Three halves x t squared minus 2t.
That will be evaluated from 1 to 4. What's 4 squared?
16.
1 squared.
4.
16 minus 1.
16.
4 minus 1. Ends up being what? 45 halves minus 6, and what is that?
33 halves?
What are the units?
Meters. Oh,
Just meters. Remember, you're going opposite now. So you remove the per unit of time. So 16 and a half meters. Does this necessarily mean that the total distance the particle traveled is 16 and a half meters? Not necessarily, right? Because remember, displacement and total distance are different. In this case, they happen to be the same because your velocity is positive over 1 to 4. So we'll give you the total distance. But in general, if instead it asks for total distance, you just integrate the absolute value. Right? Just like the difference between area, signed area, and total area, remember that? Signed area was just the integral. Total area was the integral of the absolute value. It's the same concept. So we're being told that water flows into a tank at a rate of 5 plus 2t liters per minute, out at a rate of t liters per minute. We're also told that the initial volume is 200 liters. They want us to find volume after 6 minutes. Well, again, we're going to use net change. V of 6 would be V of 0 plus the change in volume, right? But the change in volume would be that integral, right? What is dV dt? Right, it's the rate of change of volume, but what is it for this problem? What's the exact change? How's the volume changing?
Is it 5 plus t?
How'd you get it?
Because the rate n is 5 plus 2t, and then it's losing 1t at the same time. So
Just the amount flowing in minus the amount flowing out, right? Well, they told us V of 0, right? 100 liters. Now our change, integral from 0 to 6, 5 plus t dt, and keep in mind that that change is going to be measured in what?
in liters.
Just liters. So I'm not writing it out just yet, but keep in mind that that will be liters. Which makes that expression make sense, right? You can't add different units, right? If I said 200 meters plus 40 seconds, that makes 0 sense whatsoever, right? It'd be like, you have $1 million and add 8 hamburgers to it. Give you an idea of how nonsensical that is. First question would be, what kind of hamburger? Are we talking about cheap-ass McDonald's hamburgers, or are we talking about like the Japanese Rankin burgers? Where each burger is probably like $300. Burger, I'm not using the right cube that costs $500 a pound, whatever it costs. That's like I'm just having a steak and I just want to bite into it. Integral of 5 plus t.
5t plus t squared over t.
And that gets evaluated from 0 to 6. What is 6 minus 0
6
times 5?
30.
6 squared. 0 squared. 36 minus 0 divided by 2.
80.
So what is our final volume?
248 liters.
There you go. So after 6 minutes, there's 248 liters in the tank. Maybe. Because we just made a fatal assumption here.
Oh, we don't know how the tank is.
We're assuming the tank has infinite capacity. For all we know, maybe that only has 215 liter capacity. In which case, it's not going to have 248 liters. You're going to have overflow. So we're assuming infinite capacity. This is a very similar problem, except in terms of population. So fish population is changing at a rate of 120 minus 16 minus 30, and it's written that way for a specific reason. fish per month. 120 minus 6t is the growth rate, so that's their reproduction. I'm assuming no deaths in that time.
No migrations either.
30, well, constant harvesting. So I'm assuming it's a farmer, they're not going to swim away.
Yeah.
Right, 30 is the constant harvest rate, so every month they harvest 30 fish. That's why I think we can pretty much safely assume no deaths. Although maybe that 120 minus 60 is already accounting for that. It's possible. Initially, there's 5,000 fish. Find how many fish there are after 10 months. Again, this is a net change, right? P of 10 is P of 0 plus our change over the 10 months. dP dt, 90 minus 6t. What is the integral of 90 minus 6t?
92 minus 3t squared.
And the fact that that's 0 to 10 makes this really nice. 10 minus 0 times 90.
900.
10 squared
100.
minus 0 squared. Now, what's 3 times 100? What is that fish population?
1100.
After 10 months, there's 5,600 fish. That means they're not going to be out harvested. Now, again, there is an assumption here.
Like physical capacity.
Infinite capacity. Well, I'm assuming that the growth rate is taking into account the deaths. Generally speaking, the growth rate will account for deaths. Obviously, if there's limited space, there is going to be a population cap.
Oh, and also food.
That counts into the population cap. So that's all built into a population cap. Bleecker studied that way more in differential equations.
There's a population section and
It's generally studied as a hunter-prey model, and the prey will have a population cap based on external factors. So you account for that in hunter-prey models, and those are still totally simplified. Now, I believe we looked at part 1 of the fundamental theorem earlier, like the 2 problems. Oh, they were easy. Let's throw in a second speed bump. non-constant limits. Find f prime and evaluate it at 0. Well, aren't we allowed to do this? Just pick a value between, or pick a value in an interval, and you can split your integral. Well, that second integral now satisfies the first part of the fundamental theorem. Right? That first one doesn't, does it? Has to be a to something, right? Not something to a.
Oh, so you just flip.
Can't you just flip the signs and multiply by negative? So isn't this the same as this? Each of those integrals now satisfies the first part, right? And remember, differentiation is linear, so you can split it across sums. And I'm not going to write out the u's, this is chain rule, right? So for that first one, the derivative, wouldn't it be the square root of 1 plus e to the x to the fourth power times the derivative of e to the x, which is just e to the x, minus square root of 1 plus x squared to the fourth, right? Times the derivative of x squared, which is what?
2x.
What is e to the x to the fourth power?
E to the 4x.
X squared to the fourth.
X to the
There's your derivative. Evaluate that at 0. What is e to the 0?
1.
Okay, this asshole keeps calling me but never leaves a message, so trying to scam me. So then that's just 1, right? What's that?
1.
What is this entire first term at 0? What's 0 to the 8th power?
Doesn't matter.
It does matter. 0 times an undefined number is undefined.
What's root 1?
Right, so 1 plus 0, root 1 is definitely defined, right?
Yeah.
So you have 0 times something defined. So your answer is root 2.
That second term is equal to 0.
Yeah, because it's 0 times something that exists.
Yeah.
It's 0 times a real number, which is 0. Technically speaking, you got a negative under that square root, it would still be 0. 0 times any number is 0. But for our purposes, it wouldn't be defined. value of this function on the 0 to 3? Now let's just make life a little bit easier. Rewrite the function as piecewise. Absolute value of x, that's a piecewise function, right? What is it? So what's the definition of absolute value of x?
X and negative x.
What are the conditions?
Greater than 0 and less than 0.
You're missing one.
Oh, greater than equal 0.
So we can kind of do the same thing here. And then simplify. FOIL. X minus 1 times 2 minus x, FOIL that out, what do you get?
So negative square root plus 3x. And then minus 2.
If x minus 1 is greater than or equal to 0, what is x? And you don't need to do any more work. Second piece would just be negative top piece, right? And x less than 1. There's our function. Now we want average value. Is it supposed to be 0? This interval, though, look at the piecewise function. Where is it splitting?
On 1.
Is 1 in our interval? So doesn't our integral have to split? Yeah, because I used 1 instead of 0. But 0 to 1, what's f of x?
X squared and minus 2x plus 2.
One to 3, what is f of x?
No, it's the same. So negative x squared plus 3x minus 2.
Integral of x squared minus 3x plus 2.
Is 0.
just want an integral. I don't want the evaluation. I want the antiderivative.
Oh, oops. Yeah, I got you.
1/3 x cubed minus 2 3/2 x squared plus 2x.
That piece there goes 0 to 1. Now, instead of doing plus, let's do minus.
And then is it the same?
Because now the antiderivative is going to be exactly the same, isn't it? The only difference is that piece will be evaluated 1 to 3. One cubed.
1.
Oh, this one's nice. Because each of those, x cubed, x squared, and x from 0 to 1, is not just going to be 1. Three cubed. 8.
No, what's that?
1 cubed.
1.
27 minus 1. Divided by 3.
26 over 3?
Or 8 2/3. 3 squared.
No.
Minus 1.
1. Oh, 8.
What is 8 times 3 halves?
12.
3 minus 1. 2 times 2.
4.
Let's see how good I am.
I trust you. I'm not taking that.
Wow.
I guess I could.
I mean, have a calculator on.
Yeah.
I figured that might be the easiest.
Yeah, I don't know what else to do. I trust you now.
It's obviously one negative 1 over 18. Okay. Get that just by looking. That inside clearly simplifies to negative 1/6. That's so obvious. I just multiply by a third and you get your negative 1/18. There's our average value. So there's nothing different, right? It's just more parts, but the process itself is still the same. So far, nothing super out there, right? Still shouldn't be anything terrible. Just volume again. Right, so we have inflow, we have outflow. We have an initial volume, and they want us to find 4 things. We'll start with A. They want us to find volume after 3 minutes. Well, again, that's going to be a net change, right? So let's first look at dV dt. What is the change in volume? How does volume change?
Is it 1 plus 2t minus 3 e to the negative?
In liters per minute? Well, then the volume after 3 minutes will just be what? Initial volume plus the change in volume of those 3 minutes, right? What was V of 0? 100? What's the integral from 0 to 3? 1 plus 2t minus 3e to the negative t. What is the integral of 1?
T.
What about 2t?
T squared.
Now 3e to the negative t. E to the negative t is not one of our basic forms. So let's just think about it. Remember what an antiderivative is. What function has derivative e to the negative t?
E to the negative t.
Negative e to the negative t. That's your antiderivative. Multiply that by negative 3. And there's your integral. Right, we'll see how to do that without having to revert to antiderivatives Thursday, actually. Sure. 3 minus 0.
3.
3 squared. 0 squared. What's the difference? What is e to the negative 3? What is e to the 0?
1.
So that evaluation must be e to the negative 3 minus 1. Simplify that.
Plus whatever minus
Right? What's 3 times negative 1?
negative 3.
Plus 12.
9.
So that'll be your final volume. Right? That was just A. What are they asking for in B? Total volume added over that time interval. Well, volume added would be the volume that flows in, right? How would you determine that?
Can't you think the difference of what we just found?
That's a net change. That's not what they're asking for.
Okay.
They're asking for over that 3 minutes, how much volume flowed into the tank.
Oh.
Do you take the derivative of the
Derivative?
I mean, antiderivative.
No, not an anti, just integral from 0 to 3. Antiderivative would be if there aren't any terms. It would just be that, right? You're integrating the inflow rate, which was what, 5 plus 2t?
Yeah.
What is that integral? So antiderivative of 5 plus 2t?
5t plus t squared.
Five times 3,
15?
15 plus 9,
24
and it's 24 what?
liters.
So over those 3 minutes, 24 liters flowed in to the tank. What was C asking for? Volume removed. So how much volume flowed out, right? Well, how would we find that?
It's the same, but instead of things out.
What was the outflow?
Four plus 3 is the negative.
What is that antiderivative?
4t, is it minus 3e to the negative t?
That gets evaluated from 0 to 3. Uh, 3 minus 0 times 4. And then that's going to be that, right? What does that simplify to?
9 times 8 and negative 4.
Not times. Should minus the 3 e to the minus 3, right? And should it be 9?
Oh, it's just
Oh, I know you're adding 3 to it.
Right, because it's negative 3 times negative 1. And that's in liters. And D is asking for net change. 2 ways. Be the inflow minus the outflow, right? What was that?
9 plus
Or the integral of dv dt, but wait,
oh, it's the same.
wasn't that piece right there? Well, wasn't that the 9 plus 3e to the minus 3? Same thing? That means we did math right. And if it was different, we'd be in trouble. Good. So nothing super complicated, right? Fundamental theorem, any questions? Pretty straightforward. So like I said, that was 2 sections covered, 5.3 and 5.4. So you have 2 homeworks, one on just the fundamental theorem and one on net change. Thursday, we cover 3 sections, 5.5, 5.6, and 5.7. So they're all kind of just tied together, which is the most basic technique of integration known as U substitution, or change of variable. Well, it's a change of variable. And that's going to allow us to do some more interesting antiderivatives. Then there's only 1 section left after that, and that's area between curves, which is 6.1.
Oh, that'll be next Tuesday.
That'll be next Tuesday.
So what's the plan Thursday?
Review worksheet
Oh, okay.
for the final exam. So that Thursday will just be the entire class will be the review worksheet, not being without on it. The final exam. Don't forget your last project is also due, what is it, next Tuesday? I think that is right, yeah. So on the syllabus, I do have the date, right? It's the 16th. Which is 2 weeks from today. The start time is 3 o'clock. It's a 2-hour block. So on the 16th, we'll be in this room from 3 to 5 for the final exam. And unfortunately, I do have to make it comprehensive. So it is a comprehensive exam. It covers everything. Not that it matters for this week, but all assignments will have to be turned in by the final exam. So the 1 week extension may be shorter. So it has to be done by the 16th.
For the homework that's going to be assigned next Tuesday.
That doesn't affect. Well, it affects it a little bit because it'll have to be turned in by 3 p.m.
Okay.
The 16th. So you lose 40 minutes.
Okay.
But homework on Thursday, which I don't think there will be, would be cut short. Also, the Unit 4 test will be available next week. I have it set to be due Monday, the 15th, by the end of the day, so that solutions can post before the final. So solutions will post Tuesday at midnight, right after the due date. So at least you'll have a little bit of time to look over those solutions for the final. Otherwise, I was originally going to have it due before the final by 3 p.m., but I'm like, I'll make it the 15th and let you at least see the solutions. but more on that next week.